things. And in readiness for our CAT, last week we missed one class. And yes, on Monday, because of the holiday, we didn't have a class. So I will request us that we schedule another class so that we can cover two things that are part of the CAT next week. And then you will need to cover them in our Okay, so we are going to look at the gas laws. And the kinetic theory. So if you remember from our previous topic, we were looking at we were covering the topic of thermophysics. And in thermophysics, we basically looked at the fact that when two objects are in thermal contact, they exchange heat. When the heat is exchanged, it affects both systems. The system that is losing heat may have its temperature reduce. The system that is gaining the heat will have its temperature increase. Sometimes instead of the temperature increase, we may have a situation where the systems change state from gas to solid to liquid, or liquid to gas, from solid to liquid, or liquid to solid, whichever the case may be. So this is what we looked at. We also considered in detail how the temperature increases, and we looked at the specific heat capacities, how much of the substance changes phase. We looked at the latent heat capacities, both of fusion and of vaporization. We also finally ended with the transport of heat, and they considered how heat is transported by either conduction, which involve vibrations, and collisions of particles within the substance. We also looked at by convection, which involves the movement of particles from one region to another and thereby transporting the heat, or by radiation, where the actual radiation, the heat radiation, the photons, the particles of heat are moving from the hot place to another, and such as from the sun to the earth. And earlier, before we even talked about that, we started off with the fact that when a heat is added to a substance, it will change size. For example, a solid may become longer than it was when you add heat. When you take away heat, it may become smaller than it is. That was more expansion. We also said that if it was a liquid or a gas, they would occupy larger space when heat is added. And so the topic of the gas laws has to do with thermal expansion of gases. So in this topic, we are focusing the thermal expansion of gases. This arises from changes in thermal conditions. When we have changes in thermal conditions. So the same way that we define the coefficient of thermal expansion for solids, this time around we are going to look at gases, since we cannot measure their length or their area, but we can measure that they were occupying a smaller volume. And if we have a movable pistons that can allow them to push things, they will be able to push something so that they occupy a larger volume when they expand. And so, in general, when we have a system that involves gases, it is important for us to be able to define or stating the state of a system, the state in which the system is. Let me give a practical scenario here where suppose my system is a container containing a gas. There is a gas here. The question is, what is the state of this system? This is the question we want to ask. What is the state of this system? To be able to explain the state of the system, we need state variables. We need what we call state variables to properly describe the state of a system. So to properly describe the state of a system, we need what we call state variables. The state variables are the following. We need to describe, number one, we need to describe the pressure. We need to state the pressure of this gas is so much. And as we know, pressure is simply given by the force over area. And we know how pressure is measured using barometers. We can connect this to a barometer and we can measure the pressure. The same as when you go to a hospital and you are being diagnosed, you are like a system, and someone is trying to determine, the medical practitioner, the doctor, is trying to determine the state, your state. Are you in good state of health? One of the state variables that they are going to use is to measure your blood pressure so that they can determine that, no, you're not in good state. You're not in healthy state. You are in an unhealthy state when your pressure is not normal. So pressure is a state variable. The SI unit of pressure, as you know, is Newton per meter squared or pascals, which are the units that we use to measure pressure. A second state variable that helps us understand the state of a system, and this happens even when we go to the hospital, when they want to determine the state in which you are in terms of health. We also have temperature as a state variable. It helps us to determine, is someone in good state of health? We want to determine the state of this room that I'm in. In what state is this room? We must measure the temperature. Then we can say, no, it's too hot or it's too cold. Sometimes you want a room to be slightly hotter than it is. So you want to determine, no, this is too cold for a patient to stay in such a room. So we want to measure the state of that system. And of course, we know that this gives us the amount of heat that is present in the room. A temperature, as we have seen it, is measured in degrees Celsius or Kelvin. We also saw how it can be measured in degrees Fahrenheit, and we can convert between all these different steps of units. But the common one is Kelvin or degree Celsius. The other important state variable that gives us is the volume. Volume is a state variable. We use capital, and volume is measured in meter cubed. This is simply how large the size is. If you put air in a smaller volume compared to putting it in a larger volume, even the pressure itself will be affected. Instead of volume, we can also measure the density, because volume is simply the amount of space available. So volume is in the amount of available space. How much space is available? Density, on the other hand, it can either be the mass density, which we use the rho, and we know this is given by the mass over volume, or it could be the number density. Which is, we are going to use the symbol capital N for number density, which is equal to number of particles over the volume. So mass density can exist, can either be expressed in terms of the number of particles, the mass, the amount of substance in terms of mass over the volume, or it can be expressed in terms of the number of particles present over the volume. For example, we can even convert between the two different densities, because each particle has mass. So if we combine the masses of these particles and add them up, we can then express the number density into mass density. So this is the density. So in short, when we specify the density, in a way, we are also specifying the volume, because we can express we can make the volume the subject of the formula, or we can make the volume here subject of the formula. So meaning volume, we can either be given the actual volume or the density, then the two will give us the state of the system in terms of the available space, the number of particles that are present, or the available space for the mass of the substance that is available. So we have a particular mass, and we want to determine how many particles are available. So this is important. We will also generally, let us also take note that the number of particles will generally also be the number of moles. So the number of particles, we like to use the small letter n, which is simply defined as the number of moles. So when instead of just mentioning number of particles, we like to express it in terms of number of moles present in the substance. Yeah, so this is how we are going to, these are the three important variables that will express the state of a system. They will give us the state of a system. Once we have these particles or these variables, we are able to tell in what state is the system. Let's just do a quick example. To apply what we've just covered right now, we say estimate the total weight of the atmosphere using your knowledge of parameters and the given radius of the Earth. Of parameters and the given radius of the Earth. I will quickly do this for us. You know what we have is we have the Earth. It has a radius from the center of the Earth. We have the radius of the Earth, for example, and then outside of the Earth we have the atmosphere. Here is the atmosphere. Let me just indicate that this is the atmosphere of the Earth, and here I'm going to put this is atmosphere. The question is, what is the total weight of the atmosphere? Now, if you remember very well, pressure is given by force over area, and the surface of the Earth we have P atmospheric pressure, which is given by 1.013 times 10 to the power 5. So meaning the pressure at the surface of the Earth is known. This is the pressure at the surface of the Earth. The pressure at the surface of the Earth. So the entire atmosphere is applying a force at the surface of the Earth. Therefore, at the surface of the Earth, we have atmospheric pressure is equal to force over area. Since we have the radius of the Earth, we can determine the surface area of the Earth, where this is the surface area of the Earth, and it's given by area will be equal to I it will be given by 4 pi r cubed, 4 pi r squared, rn squared, like this. Therefore, the force, making the force the subject of the formula, which is going to be the weight of the atmosphere, is equal to the pressure of the atmosphere than the surface area of the Earth. This is going to be equal to atmospheric pressure multiplied by 4 pi radius of the Earth squared, like this. We can put the numbers there to determine the weight of the atmosphere. Now, I want to take our study further. Remember, please don't forget that our focus of the study today, the focus of our study today is we are focusing on the thermal expansion of gases in the face of atmospheric changes, in the face of changes in conditions. And for us to state this system, we have defined the pressure, the temperature, volume or density as the variables that give us the state of a system, meaning that when we have thermal changes in the system, either of these particles will change. For example, when you are feeling sick, malaria, you have some malaria parasites in your body. Then the body will react by beginning to manufacture more white blood cells to fight the malaria. As this happens, there are more chemical reactions, and at the end of each chemical reactions, as you have learned in chemistry, one of the products is energy. And so this energy comes out in form of heat, and so you find your temperature increases. No wonder the doctor at the hospital will check your temperature, determine the state of your body, whether it is in good state of health or in bad state of health. So it can also be pressure that will change. All of those are systems that are checked to ensure that we can determine that you are in good health or state of health. Let us also note that in this topic, as we discuss, we are going to meet a lot of physical constant. There will be a number of physical constants that we are going to encounter. Let us first quickly list them. We are going to encounter a physical constant called the Avogadro's number. We are going to use it quite a lot. The Avogadro's number, we use the symbol capital N, a subscript A. This is simply the number of moles contained, the number of particles contained in 1 mole of a substance. The number of particles contained in 1 mole of a gas. And here, let me just use gas because after all, we're dealing with gas laws. And the number of particles contained in 1 mole of a gas is equal to 6.022 times 10 to the power 23 molecules. Just give me a minute. I address one quick comment. Okay, so this is the one physical constant that we are going to encounter in this course. The second physical constant that is important in this topic is the universal gas constant. The universal gas constant, we are using the symbol R for the universal gas constant. It has a value of 8.314 times 10 to the power, just 8.301.
Sir.
Yes, please.
Sir.
Yes, please. You can go ahead.
Where is the 4 pi r squared coming from?
What?
Where is the 4 pi r squared coming from?
It's coming from the
4 pi r squared.
okay. The area of a sphere is given by 4 pi r squared. When you have a ball, like a football, the area around the football, that surface area of the football is given because it's a sphere. It's a sphere. The surface area of a sphere is 4 pi r squared. I was giving you the physical constants that are of interest. We started off with Avogadro's number. We have made this constant already in our chemistry class. It is also important in physics. Actually, it is the physics people who discovered it and they found out that there are that many particles in a mole of a substance. The next important quantity is the universal gas constant. We are going to use the symbol capital R for this, and it has a value of 8.314 joules per mole of a substance, Kelvin. So this is the universal gas constant. I will explain later on how this constant was discovered when we look at the gas laws. Another constant of interest, which is the third constant, is the Boltzmann's constant. Or maybe before we talk about the universal gas law, it is also, before we talk about the Boltzmann's constant, you can express this in other units, such as 8,314 joules, 314 joules per kilomole. Per kilomole Kelvin. So when you put kilomole Kelvin here, we have multiplied this by 1,000. We have this many particles, which is I think we'll just end it that we can either express it in terms of kilomoles or in terms of moles. Then the next one is the Boltzmann's constant. It is also important. Boltzmann's constant. The Boltzmann's constant is another important quantity. We use small letter k with a subscript b, and the Boltzmann's constant was discovered separately, but it was later on found out that it is simply equal to R divided by the Avogadro's number, and its value is 1.3807 times 10 to the power minus 23 is expressed in joules per Kelvin, like that. Now we can venture into the gas laws. We can look at the actual gas laws that we were talking about. Now that we've discovered, we have talked about the important variables that we must know for us to be able to explain gas laws. First and foremost, gases are unique. Gases are such that when one of the three state variables changes, the other two may also change. Kindly mute your microphones. E.g., we have temperature, volume, and the pressure. So when you change the temperature, the volume and the pressure can also change. Kindly mute your microphones. Somebody has left their microphone unmuted and it is disturbing the class. Okay. So this is the nature of gases. When the temperature, when we're looking at solids, it is possible to just keep the pressure of the solid the same. You simply allow the temperature to change and you measure the length, which changes the volume of the solid. Now for the gases, all the three change. And so there are different laws that were found, because for people to find out how these are related to each other, they had to keep one constant. So we find out that the gas laws explain how these state variables are related to each other. That's what the gas laws do. The first gas law we are going to deal with is the Boyle's law. The names of these laws are related to the names of the people that discovered the laws. What Boyle did was to keep temperature constant. He kept temperature constant and allowed the volume and the pressure to change so that he can find out the relationship of the pressure and the temperature. Keep temperature constant, see how pressure and volume are related. So you carry out the same experiment under the same temperature conditions. You ensure the temperature is not changing and you are changing the pressure to see how the volume is going to change. You change the pressure to see how the volume is going to change. And Boyle discovered that the pressure that is exerted by a gas at constant temperature is inversely proportional to the volume in which it is enclosed. Sorry. Hello? 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 Hello, good morning. Hello, good morning. Hello, good morning. Yes, please. Hello, good morning. I'm fine, and how are you? Oh, okay, okay. Yes, I was trying to confirm our exam is tomorrow afternoon, isn't it? Is our exam tomorrow afternoon? Oh, okay. Sorry about that short break. Okay, so the pressure exerted by a gas at constant temperature is inversely proportional to the volume in which it is contained. This is Boyle's law. What this means is the pressure exerted by a gas at constant temperature is inversely proportional to the volume in which it is contained. When we cross multiply this, it gives us pressure times. So in short, this is when we remove the proportionality symbol, we have pressure is equal to constant of proportionality times 1 over volume. Then when we cross multiply this, it gives us pressure times volume is equal to a constant. What this simply means is that when we have the volume of a substance, and then we now increase the volume of this substance under the same temperature. This experiment is we are changing this to change to that. This we had volume 1, it has been changed to volume 2. What this equation states is that even the pressure will change. Here we had pressure 1, even the pressure will change, pressure changes to a new value, P2, and the change is such that when we multiply pressure 1 and volume 1, we multiply these two quantities, the answer is going to be the same as the pressure 2, volume 2. So the pressure and volume will change. The moment you change the volume, you make this bigger, the pressure will automatically change, and the change in the pressure will be such that the product of the pressure and the force here and the product of the pressure and the force here is the same. This is the Boyle's law. We can do a quick example in air bubble. The volume of 1.5 centimeter cube the volume of 1.5 centimeter cubed when it is released by a swimmer. 100 meters below the surface of Lake Kariba. Let's not call them a swimmer. The swimmer doesn't swim at this depth. Let's call them a diver. Because the swimmer cannot be that deep. So it's a diver 100 meters below the surface of Lake Kariba. What is the volume of the bubble when it reaches the surface? What is the volume of the bubble when it reaches the surface? And as we do this, let's assume the temperature and the number of moles in the bubble, the temperature in the lake, and the number of moles in the bubble remains constant. So let's assume this. When we do this, we will use, so in short, we have the water. Here is the water in the lake, and this bubble is being released by a swimmer who is 100 meters below the surface, and the bubble begins to move up like that. We need to determine the pressure 1 here, and we have been given that the volume 1 is equal to 1.5 centimeter cubed. The first important thing is that we must change this, and I leave it to you to change this to a meter cubed. What is it in meter cubed? It's given in 1 centimeter cubed. What is it in meter cubed? At the top here, we know the pressure is simply the atmospheric pressure here. The question is, what is the volume 2? Pressure 2 is atmospheric pressure. What is the volume 2 here? The pressure here can be found because we know the pressure at the bottom of a fluid is equal to the fluid pressure plus the atmospheric pressure, which is equal to rho g h plus atmospheric pressure. So this is the pressure at the bottom here. Therefore, we can use the volume pressure 1, volume 1 is equal to pressure 2, volume 2. Where pressure 1, we have found it to be this. Volume 1 is given as this. Pressure 2 is atmospheric pressure, which is 1.103 times 10, 113 times 10 to the power IV pascals. The only unknown here is the volume 2. We can make volume 2 the subject of the formula. Pressure 1, volume 1 divided by pressure 2. So you can complete this activity. The next gas law that we are going to consider is I'm going to combine two laws at the same time. I'm going to combine two laws. We are going to talk about the Charles and Gay Lusek. The Charles and the Gay Lusek law. This is a combination of two laws. Here we are going to have at constant pressure so we want to keep pressure constant, a volume of a gas, unit temperature remains constant. The volume of a gas per unit temperature remains constant. I'm trying to be different from first year, no, from grade 12. In O level, you learned that you learned them as separate, Charles law and the pressure law. So here now I just want to combine them so that at least we feel like we are in university. We are learning something slightly different from what we did in high school, more advanced. So basically what we are saying is that when we keep the pressure constant, the volume per unit temperature remains constant. That means at constant pressure, the volume over temperature is equal to a constant. It simply means that when we operate under constant pressure, we have a system here. There is V1, T1. Then we have the system where we change T to T2. The volume will also change to V2 such that, so here we have these changes such that the volume over temperature 1/1 is equal to the volume 2 over temperature 2, like that. As long as this is done at constant pressure. It is also important to note that at constant volume, if we keep the volume constant, the pressure is inversely proportional to the temperature. Pressure is inversely proportional to temperature. Just a minute. So, sorry about that short break. I wanted to state that when we keep the volume constant, the pressure is directly proportional to the temperature, meaning that the pressure divided by the temperature is a constant as well. Now, what we have here, we have looked at a number of laws where we have either kept pressure constant, we have kept volume constant. Here, let me use a different color. We have kept volume constant. We have talked about keeping pressure constant. We have talked about keeping a temperature constant. keeping temperature constant. So we are looking at these variables and how when one is kept constant, you allow the other two to change, then you find the relationship between the two that are changing. That's what we are doing. So the first we did temperature constant, the second we have done pressure constant, the other one we have done volume constant. Each one of them, we have seen that when we now, so in short, we have the first one is pressure times volume is equal to a constant. We have talked about volume divided by temperature is a constant. Hello? Hello? Yeah, I'm in a class, I'll call. And we have also talked about the pressure over temperature remaining a constant. So now we have formed three constants. We can combine these constants. How we combine them, whether it's by multiplication or by division or by whatever combination you do, we don't know, but we know that when you combine constants, it's not as complicated. So when these constants are combined, we have a situation where pressure times volume divided by temperature is a constant. This is what combining these three equations gives us. And we now call the equation that gives us this, we call it the equation of state. Is the equation that combines all the three variables. The equation of state is the equation that relates pressure, volume, and temperature. And remember, the volume can come out either in number of particles or in number density or in mass density. You can either express it in those two, but generally it relates these three. And we've seen that the pressure 1, volume 1 over temperature 1 is equal to pressure 2, volume 2 over temperature 2, meaning that when you have a system with the pressure 1, volume 1, temperature 1, if you just change any one of these, the other two will also change to new values so that this product and this product is a constant. Now, if the gas involved, our class is going to end in about 10 minutes, and then we'll pause in those 10 minutes and rejoin the class. If the gas is an ideal gas, if the gas is an ideal gas, we will see that then the constant that we talked about here, this constant has a particular value. So then if the gas is an ideal gas, then PV over P is equal to a constant where this constant is equal to number of moles times the ideal gas law. If the gas is an ideal gas, then the constant that we have here is that. So that for an ideal gas, PV is equal to NR times T. What is an ideal gas? What is an ideal gas? I'm going to leave this as a homework for you to be able to describe an ideal gas. Ideal gas. What is an ideal gas? You must explain 5 properties of an ideal gas as a homework. What are the 5 properties of an ideal gas? You must talk about the separation between particles in a gas. You must talk about the random motion of the gas. You must talk about the interaction. How do particles interact in an ideal gas? You must talk about collisions. How are collisions in a gas? You must talk about the composition of the gas. So these are the 5 properties of the gas. The 5 properties of the gas relate to the separation between particles in a gas, the random motion. It has to do with the interaction of particles. It has to do with the collisions of particles with each other and with the walls. It has to do with the composition and the homogeneity of the composition. Homogeneous. So you state the homework, find out what are the 5 properties of an ideal gas, and they are related to these 5 things that I've just mentioned here. And so we have just seen that for an ideal gas, the ideal gas law, which is the equation of state, is given by PV is equal to NRT, where if the gas has the properties that we mentioned above here, then we have the constant being number of moles times, we know this is the pressure, this is the volume, this is the number of moles of the gas, this is the universal gas constant, and this is the temperature of the gas. And we will focus our attention only on this form of the ideal gas law, and the ideal gas law can also be expressed in terms of a number of particles, in terms of mass density, but will not go into the different forms of the ideal gas law. Let me give you an example which I'm going to leave for you to work with. Let's take a popular as an example. A popular band that plays music, or no, okay, maybe let me change. Let me use a new brand of cola. I don't know whether it's Pepsi Cola or Coca-Cola, but this is a new brand of cola, contains 6.5 grams of carbon dioxide. In 1 liter of the drink. The evaporating carbon dioxide is trapped in a cylinder at 1 atmosphere. If the evaporating carbon dioxide is trapped in a cylinder at 1 atmosphere and 20 degrees Celsius. At 1 atmosphere and 20 degrees Celsius. What volume does the gas occupy? What volume does the gas occupy? So I want you to do this by yourself and find the new volume that the gas will occupy. You will need to convert the number of moles. You need to find the number of moles present in carbon dioxide. How many moles are present in carbon dioxide for you to be able to use this equation that we have developed here. Once you find, okay, so I was saying that here you need to use the formula PV is equal to nRT, where from the question we saw how P is given, R we already know it, P we are given is 1 atmosphere. We are being asked to determine the volume, but then we are given the mass. We have mass from which N can be determined. And remember that the number of moles is equal to mass times the molar mass. So it's simply the mass times the molar mass of the gas. So the molar mass of the gas, we can remember it from your chemistry. You'll be able to determine the number of moles when you check it out. And now I just want us to look at one more concept, which is the kinetic theory of gases. The kinetic theory of gases. The kinetic theory of, of gases simply deals with pressure that a gas exerts arising from the regions of the gas with the containing force. Hello? Hello, good morning. Fine, thank you. Okay, let me meet you at 10 hours. Thank you. So with the containing walls, the kinetic theory simply deals with, for example, we have a gas in a container. We have the gas in a container. We have molecules that are moving about in the container. They are moving in all different directions. When they reach the container wall, they will collide, and they were moving in this direction. Then they will collide and begin to move backwards like that. And so as they collide with the container, there is a force over area that is exerted here, which simply gives us the pressure. So depending on how many particles there are, then we can find the pressure in the container. And so when we analyze the kinetic theory of gases, the result of the kinetic theory of gases, without explaining the details of the kinetic theory, what we are interested in is the result of this analysis gives the fact that thermal energy in a gas is equal to the average kinetic energy of the molecules. Is equal to the average kinetic energy of the particles. The particles can either be molecules, or meaning that the thermal energy is equal to average kinetic energy of the particles. And then when we do this analysis, we find out that the thermal energy is given by 3/2 Boltzmann is constant multiplied by temperature, and this is equal to the average kinetic energy of the molecule. So this is the result of the kinetic theory of gases. So the kinetic theory of gases simply states that the thermal energy, so this is thermal energy, and this is the average kinetic energy. This is the kinetic theory of gases. I will not explain in detail how the 3 over 2 kb times t comes. This, what we would need is, I'll give this equation in the test or in the exam, because what I want is for you to simply learn that the thermal energy is equal to average kinetic energy according to the kinetic theory of gases. And for the gas laws, I will leave it at this point for now. We will simply leave it at this point, which now at least it has given us the value of the thermal energy in a gas. How much thermal energy is contained in a gas? This gives us the amount of thermal energy in a gas. And this allows us to look at the next study, the next topic, and with that definition, our next topic, which is also going to be part of the test that we are going to write, is in thermodynamics. Thermodynamics. And so, in terms of this topic, what I want us to do is we are going to start it now. And when we start it, I want us to create time. Last week, for some reason, we didn't meet on a Monday. For personally, I forgot. We only had our online class on a Tuesday or on a Wednesday. Yesterday, because of the public holiday, we didn't, the day before yesterday on Monday, this last Monday, we didn't meet because of the KK day. And so we have those 2 hours that we need to just discuss thermodynamics so that we are ready for the test next week. But what I'm going to do also is that I'm going to share with you the recordings of the class so that even as we study this topic, we will study it knowing very well what we are, after having gone through your own self-study of the topic. I'm going to also share the notes of this topic, thermodynamics, as well as the recordings where I was teaching a class like yours, so that you are ready to do the test next week. And then this week, we are going to do a quiz. This time around, I'm announcing it in advance, so we will arrange with Mr. Mazimba and do a quiz. And the quiz is going to be based on thermodynamics and the gas laws. So it is important. Let's go through the thermodynamics. My wish is that if it was possible, we can have our class this evening. We can start it at 19 hours or at 18 hours so that we do the thermodynamics topic. And then you then are by yourselves to be able to go through the topic and do the examples that are given in the notes. So in the remaining time, I want us to introduce this topic of thermodynamics. And in this regard, I'm going to start a new window. I'll stop sharing this window and I'll share the new one that I've created for the new topic of thermodynamics. And thermodynamics. So, under the thermodynamics, it is important for us to understand that this is the area of physics that is concerned with the relationship between heat and work. We have already seen that whenever we have two systems that are in thermal contact, system A and system B, A and B in thermal contact, and such that this has temperature A and this has temperature B, where, say, temperature A is greater than temperature B, then it will move from A to B. This is what we have seen. There will be movement of heat from A towards B. This happens naturally. It's just the nature of how things happen. And so, thermodynamics involves a situation where, as the heat moves, its natural movement, we want this heat to perform work. Thermodynamics is interested in trapping the heat and causing it to perform work. We're interested in trapping the heat and use it to perform work. This is similar to the way we use kinetic energy or potential energy of water to use it to perform work. Very similar. Similar to how potential energy of water, of falling water, is used to perform work, which is simply you use it to turn the turbines at Kariba Dam. And we produce electricity. We are undergoing load shedding right now because the water that is at the high potential is limited. So electricity is produced where there is water at high height, and this water is supposed to fall to a lower height. This water is expected, when it reaches this point, it's expected to fall down and come here. Whether we like it or not, when this water is flowing here, when it reaches this point here, it will by naturally fall down. So what we do at Kariba or at Kafue Gorge is we cause this water to form work by, it is trapped by these caps in such a way that it rotates. So this now is causes the turbines to rotate in some direction. And when these turbines are rotating, the turbines are connected to the magnetic field here. There's a big magnet. There are big magnets. We have got big magnets. And because of this, say this is the North Pole, this is the South Pole, then we have the magnetic fields that go from one direction to another. So these turbines, as they rotate, they are connected to a coil where we have coiled a conductor around this coil. So as this rotates, these coils now, this part goes up, that part goes down. And we will learn later on that when the magnetic field crosses, when the conductor crosses a magnetic field, then an EMF is induced in the conductor. And then these conductors now are connected to the power lines, which bring electricity to the circuit. So we have these power lines that bring electricity to the circuit coming from such turbines. So all we are doing is we are taking advantage of falling water and the turbines so that they can turn this coil, and this conductor and these conductors are now crossing the field lines. This one is crossing upwards, this one is crossing downwards. Because of that, an EMF is induced in the conductor. This EMF then forces the electrons to move along these conductors, which travel all the way from Kariba to Lusaka. Then they travel all the way to the house where you are right now, and you have that electricity. So that's what we do. So in short, we are simply looking at the falling water, and we trap it so that it can perform work. In a similar way, we want to have the hot system. We have a cold system. If they're in thermal contact, we expect it to move. What we want to do now here in thermodynamics is we're interested in trapping this heat and divert it so that we can perform work with it. This is what happens in the engine of your car that you were driving this morning or that you'll be driving later. This is what happens in the bus when it comes to PQ. All that happens is that there is the hot system, there's a cold system. As heat moves from one to another, it is trapped and performs work. We will learn later on that we cannot use all the heat. There will still be some heat that will escape us, and there's some heat that will still go to the cold system. Now, thermodynamics is interested in the relationship between heat and work. That is what thermodynamics is interested in. And so we have the laws of thermodynamics. So far, previously, we discussed the zeroth law of thermodynamics. This is the law that we used to manufacture thermometers. It was used to make devices called thermometers. We said when a system is in contact with two systems separately, is in thermal equilibrium with two systems separately, then the two systems are also in thermal equilibrium. That was the zeroth law of thermodynamics. We looked at system A, we looked at system B, and we looked at system C. And we talked about the thermal contact, the thermal equilibrium. Then we saw how when this is in thermal equilibrium and it's also in thermal equilibrium, then these two are also in thermal equilibrium. And we call that the zeroth law of thermodynamics. And we then used this as our thermometer. So the laws of thermodynamics are important because they are used to they are applied somewhere, and we can be able to manufacture devices that we use on a day-to-day basis to manufacture things that are going to help us solve our day-to-day lives or our day-to-day needs. So now we are going to discuss the first law of thermodynamics. The first law of thermodynamics. The first law of thermodynamics, I explained to you that the first law was discovered first. Much later, that's when the zeroth law was discovered. And because it was more fundamental than the first law, it was given the name zeroth law. It should have been the first, this should have been the first law, this could have been the second law, but because this was already named as the first law, we couldn't change its name to give this one the first law, so they had to give this one the zeroth law, and this one remains as the first law. The first law of thermodynamics gives a relationship between, it relates heat and the work done and the internal energy. It relates the heat, the work, and internal energy. It states that the amount of heat added, it simply tells us that it explains how heat added to a system or removed is utilized. It tells us that when heat is added to a system, part of this heat is used to perform work. Part of this heat is used to change the internal energy of the system. So when heat is added or taken out of the system, it is used to perform work, and it is, or part of it is used to perform work, part of it is used to change the internal energy of the system. The first law states that the change in internal energy of the system is equal to the difference between the heat taken by the system and the work done on the system. Is equal to the difference between the heat taken in by the system and the work done on the system. So if you want to understand this by some diagram, you have a system. Let this system take in some heat. When heat is taken in by the system, the internal energy of the system is going to change and work is performed on the system. So there's work performed on the system. So what the first law states is that the change in the internal energy is equal to the difference between the heat and the work performed on the system. This is the first law of thermodynamics. Now, I underlined the word on here. Whenever we put W, we are talking about the work performed on the system. When the system performs work, it means that the system is performing work on the environment. The work performed by the system is positive. The work performed on the system is negative. And so the positive here is coming in because this work is a negative. The truth, this equation actually is coming from the change in the internal energy is the difference between negative work, because the work performed on the system by the environment is negative. So when we add this and this, it gives us a positive. Hence, we have that. Where this is the work done on the system. It is also possible that the system performs work. It is the opposite. It is the opposite of work by the system. There is work by the system and work on the system. On the system, it means, let me give an example. We have a system that is made of a piston. Suppose we have this system here, and we have, say, a piston that is moving here. So if you push this piston by a force, you are performing work on the system, because this piston is going to move from here to there. For example, if it moves from there, it has moved some distance, x, then we can talk about force. The work performed on the system is equal to force times displacement. So we can calculate this work that has been performed on the system. So the work performed on the system, then this is different from if we had a situation where this is work done on the system. If we had a scenario now where we have this movable piston on the other hand, and now we have the system is actually pushing this. Let us have the system is expanding, and as it expands, it applies force on this, such that the piston moves from here goes somewhere here. When the piston has moved away and covered some distance x, then this now is in work environment, because this is equal to force that the system is applying multiplied by x, and this is work done on the environment, or work done by the system. This is work done by the system. So there's a difference between work done on the system and work done by the system. So when work is done by the system, we put environment. When work is done on the system, we just put W without the environment. So we are going to end our class here for now, and then I'm going to arrange with our class rep so that we agree on the time when we can have another class to complete the topic of thermodynamics. But as I end the class right now, I'll share the notes immediately, and I'll also share with you the recordings of previous classes so that you begin to go through these notes ahead of the time that we are going to meet to discuss to complete this topic. Thank you.